This video is just going to be a basic rundown of what a limit is and how to find that limit using the graph and a table. So the limit of a function f as x approaches c is equal to L. What that's saying is that as some x value approaches, or as x approaches some value of a certain function, it's going to approach a certain y value. And this equal sign can be a little bit deceiving, such that the limit doesn't necessarily have to equal what the value is at that specific x value. This occurs when you usually have removable discontinuities, which will be discussed in a later video. But just keep in mind that the limit is what the function is approaching at that x value, not what the function may equal at that x value. So if we're given the example f of x equals x to the third minus 1 divided by x minus 1, and x does not equal 1, then that's just pretty much saying this graph is going to be the graph, except at x equals 1 there's going to be no y value. So to find the limit as x approaches 1 numerically, numerically is going to mean set up a table where you have your x's and then your f of x's, your y values. And what you're going to do is you're just going to, since the limit is what the function approaches at that x value, then you're just going to plug in numbers that are close to 1 from both sides. So you can start with 0.9 and then maybe 0.99, and then you can have 1, 1.01, and then 1.1. And what you would do is you would just plug in these x values into the original equation using your calculator, I would assume, and you would get answers coming out to 2.710 for 0.9. At x equals 0.99, the y value is going to be 2.970. 1, it's going to be undefined, but that's actually what you're trying to solve, so we'll just put a question mark there. 1.01 is at 3.030, and 1.1 is at 3.310. These you would just find by plugging this x value in for x to your original equation. And so if you look at your chart, then it seems that the number that seems to be the value at 1 is going to be 3, because what the left side of 1 is doing is it's getting a little bit higher with each interval, and then as you come from the right, it's getting a little bit less. And so what this, in between the 1.01 and the 0.99, it seems to be approaching 3. So that means that the limit is going to equal 3. And that's just saying that as this function approaches the x value of 1, the y value at 1 is going to equal 3. Finding the limit graphically is definitely a lot easier. I'd just use your calculator, but if not, you can always just plug in values and graph them. But bring up your y equals, and then I already have the function typed in. Graph it, and you can see that it's a parabola, and it appears that if I try to calculate the value at 1, then there's going to be no y value coming up, and that's because remember that we said earlier that this function is going to be undefined at 1. But if you look at the graph closer, then you can see that as x is approaching 1, and you trace it, then right at 0.957, the y value is going to be 2.87. And I'm just tracing the graph right now. If you go at 1.01, so just a little over the x value that you're trying to find, then the y value is just barely over 3. So you can see that at 1 it seems to be right at 3. And so that's how you find the limit numerically and graphically. Now, there are certain cases when limits do not exist, and those are these 3 cases where the limit of f of x from the left does not equal the limit of f of x from the right. So an example of that would be when the limit as x approaches 0 of the absolute value of x over x. If you graph that one, then you'll actually be able to see so as you can see at 0, the limit of f of x from the left, so from the negative values, they're approaching -1. But if you approach 0 from the right, that's actually approaching 1. And since -1 does not equal 1, then the limit does not exist. The second circumstance when the limit does not exist is when the function increases or decreases without bound. So that means when the function is approaching either positive infinity, negative infinity, or maybe even both. And an example of that graph would be the limit as x approaches 0 of 1 over x squared. So if you graph that one, you can see that there's going to be an asymptote, a vertical asymptote at x equals 0. And so when it increases without bound, that just means that it's going to be going to infinity. And it's never really going to approach or even touch this x equals 0. And the final circumstance in which the limit does not exist is when f of x oscillates between 2 fixed values. So that's pretty much saying that when the graph begins to do this towards the limit. And an example of that graph would be, this usually occurs with the trig functions, but the limit as x approaches 0 of sine of 1 over x. So if you take a look at sine of 1 over x, let me zoom in. You can see that the graph really starts to get, it starts to just jump around a bunch. And because it does that, then that's what oscillating is. It's just going to keep jumping from up and down, and you're not really going to be able to get a limit from that. So there's the three times when the limit will not exist.